Hey guys, welcome back to the Dynamics video series. This is going to be the last video before your exam 2 or your second exam. This video is going to be morely about, well, I guess we'll get into it. It's a bit of a more niche problem set, in that it's problems that appear to be rotational or appear to be either path or appear to be polar. But they're actually just X and Y problems, right? So you can just use X and Y coordinates for these instead of using the, I don't know, normal tangent or the radial and transverse components. So let's get started, right? So the particle has a mass of 2 kilograms and it's confined to move along a smooth horizontal slot and due to the rotation of the arm OA, theta equals 40 degrees. Angular velocity or theta dot is 3 radians per second, and the angular acceleration or the theta double dot is 2 radians per second squared. And then we're assuming that the particle contacts only one side of the slot at any instant, and essentially we want to figure out the normal force in the rod and the normal force in the slot. So let's label what we know, right? So we have a mass, right? Oh, that's a horrible M. We have a mass, right, which is 2 kilograms. Let me change the size of my pen. We have a mass, and that's 2 kilograms. We know theta. That's 40 degrees. We know theta dot, and that's 3. And then we know theta double dot, and that's 2. And that's about all we're given, right? And we're given this like structure here. And our goal is to try and figure out what should we do, right? So you might be tempted just initially when you see theta dots and theta double dots to just instantly start drawing like these radial components. So like NR, right? And then N theta, little n, right? But that's going to lead you astray here because there's an easier way to solve it, right? So if you notice, this thing only has one motion, right? It can only go in this general direction. So to actually solve it, we can use just regular x and y coordinates. So let's label it, right? So we have an x this way. We have a y here. And what we can do is we can start summing forces in the x and the y component, right? So let's label our forces at this point. So contact at a distance forces first, right? So we have gravity. So we have mg. And then we have 2 normal forces on this ball, right? Because it's being held in the slot by this force down, by this little bottom part, and is being pushed by the actual rod, right? So we have this normal force from the rod, which is coming out this way. Let's just call that NR. And then we have a normal force that's coming up from the slot, the bottom of the slot, because it's being pushed down, and that'll be NS, or N from the slot. All right, and then from here, I think that's all the forces we have, so we can start summing the forces. So let's go ahead and do that. So sum of the forces. Since we labeled x and y axes, we can just do them in x and y. So let's do the x first. So if you notice, we actually only have one force that acts in the x, and it acts at this angle right here. We can call this angle beta or something. We can easily solve for it, right? We're just analyzing this triangle. So we have this triangle here. Let me try and do it pretty good. So that's like where it contacts it. This is 90 degrees, and we know this angle is 40, right? So this angle right here, or the angle that contacts with this rod, right, has to be 50, right? The interior angles add up to 180, and then since we know that one is 50, and this has to be 90, just because the definition of a perpendicular normal force, then we know our beta just has to be also equal to 40. Right, so that's equal to 40. If we want to sum on the x-axis, we're going to have a positive NR, and then is it the cosine or the sine? It's the one right next to the angle, so it's the cosine of 40. And that's equal to our mass times our acceleration in the x. All right, now for the y. All right, so all of these forces are acting in the y, so let's label them first. So we have that positive normal force from the slot, minus mg, those entire components. And then we also have a bit of the nr, right? So that's also in the negative. So we have negative nr, and then since the other one was cosine, this one is going to be sine of 40. And then this thing is not accelerating in the y at all, right? Because it's in this horizontal slot, right? So it's not going to be able to move up or down. So this is just going to be equal to 0. So we have 0 there. Oh, that's weird. So we have 0 there. So let's count how many unknowns we have. We have 1, 2, 3. Oh, tough. We only have 2 equations, so it's not solvable just yet. We're going to have to solve for one of these first, right? So let's try and think, how can we solve for these knowing what we're given? What we're going to want to find is the ax here, right? How can we do that? So let's see if we can get an equation for x, right? Because we know y is always going to be 0.5, right? And it's always going to be this part of this triangle, right? This will be the y. And this part of this triangle will be the x, right? And if you look at it, this height part of this triangle is never going to change, right? It's always 0.5, right? And that's equal to, right, whatever this angle is, and the r, right? We can express it as a function of r in this angle. So if we use r in this angle, then this side becomes r, and then this is cosine of 40. And this equals to 0.5. And this top part is r sine of 40. Okay. So let's see. We can solve for r from this thing. So if 0.5 equals r cosine of 40, then r equals 0.5 divided by the cosine of 40. Oh, wait. Instead of 40, let's use theta, because this angle is changing, right? So we can't just label it at the given value. So let's use theta for both of these. So let's say this is 0.5 cosine theta, right? And that's always going to be r. And then now let's plug r, because this is equal to our x value. Is our x value, right? Because as we go, this x value is going to be the r sine of theta always, right? Just because this triangle is laid out. So if x is always equal to r sine of theta, and r is always equal to 0.5 over cosine theta, then when x is actually equal to 0.5 divided by cosine theta times the sine of theta, which actually we can just simplify as 0.5 tangent of theta. All right, so we have an equation for x and tangent of theta. It's at this point that we can start doing things like x dot and x double dot, because those directly reflect to the velocity of x and the acceleration of x, which is what we're looking for. So let's start doing those. Now you can either do those by hand, or you can do those with the algebra solver, the Mathematica. I elected to do it with the Mathematica just because I found it more time efficient, and you can do it on your exam. This is the code I used. I explained it in a video beforehand, but essentially it's just establishing your theta as a function of time, taking 2 derivatives, right, to get the x dot and the theta dot, and then plugging in your values for theta, theta dot, and theta double dot. Check out my previous videos on polar coordinates if you want to see what those are about. But let's go ahead and use Mathematica for this. When I solved it, I got that x double dot is equal to 14.57. All right, and then now we can actually plug that, because that's directly equivalent to ax, or the acceleration in the x, into our top equation. So let's rewrite it down here. So our nr times the, what was it, cosine of 40 is equal to 14.57. And then we can solve, and nr equals, calculator, what was it? I got 38.04 about. Right, and that's our normal force in the r. And then now to solve for our other normal force, that's in the slot, right? We can plug this value into this nr up here. And we do that, we'll get that ns, or this value we're looking for, minus mg, which is 2 times 9.8, minus that 38.04 times the sine of 40 is equal to 0. And then we can just move these terms to the other side and get that ns is equal to, plug it in, 44.05. All right. And then that's going to be both our answers in this case. So if you notice, for this problem, we actually didn't need to use the r's or take a derivative of it. We did need to still take a derivative of the x, but we did use the x and y coordinate system, which is kind of the thought behind these. If you see a ball moving through a slot, right, essentially is the idea, like a vertical slot or a horizontal slot, try and think about if you can use the XY coordinate system, because it's often going to be a little bit simpler. But yeah, that's all for this problem.